Welcome back to AP Chemistry. In this video, we're looking at some applications of intermolecular forces. And so, for example, here we're looking at how temperature changes as heat is added. And so let's take a look at this diagram here. And so what we can see is something that we call a heating curve. And so we start over here at the left end here of the graph, and we can see that over here we have a solid, and we're starting with a solid, and we have a very low temperature, and as we add heat, that solid is heated, and that makes sense. That's what we would expect to happen. Then we get to a certain temperature where we keep adding heat, but the temperature doesn't increase. Now we call that melting, the melting point. And so what we can gather from this is that as a substance is melting, its temperature does not change. We add heat, but its temperature doesn't go up. That heat is invested into the melting process. And the value that we associate with that is called the heat or the enthalpy of fusion. Once all of the substance is melted, it's now a liquid. And so we see this here, and we keep adding heat, and now the temperature once again continues to rise. And it does that for quite a while until we get to another point. And now we add heat, and there's no temperature increase. Rather, it's the boiling point. And so the heat or the enthalpy of vaporization is what discusses that point. So that's the boiling process. And we keep adding heat. It boils. Once it's all boiled away, we now have a gas. And when we keep adding heat to that gas, the temperature of that continues to increase. And so that is what we call a heating curve. Now we can do the opposite and take a look at this as it's cooled, and that would be called a cooling curve. In that case, the heat associated with the freezing would also be called the heat of fusion, and heat of vaporization would be associated with the condensation in that circumstance. So let's answer these questions here. Which states of matter exist during the melting process? Well, hopefully we can see that it is a transition between solid and liquid. So it would be the solid and liquid phases at that point. Next question, does the temperature of a substance change as it is boiled? Well, during the boiling process, we can see that the temperature is stable. So the answer is no for that. Now, what is the heat of fusion? Well, this is the amount of heat, the amount of energy that's required to melt, or in the other direction, to freeze. How much energy must be removed to freeze the solid or the liquid? And let's try an example with this. Here we have a problem. It says the enthalpy of fusion for water is 334 joules per gram. How much thermal energy, or as we usually call that heat, would be required to melt a 4-pound block of ice with a mass of 1,814 grams? This is just a simple dimensional analysis problem. We're going to take the mass of the block of ice, 1,814 grams, and we're going to convert that to joules using the enthalpy of fusion. So it's joules on top, grams on the bottom, and it's 334 joules required to melt every 1 gram of the ice. So of course grams will cancel top and bottom, and now we can multiply this, and when we do the arithmetic, we see the answer is about 606,000 joules. Or if we're looking at that in kilojoules, that would be about 606 kilojoules. And so that is the amount of heat it would take to melt that block of ice. And so when you buy a block of ice, normally what you're doing is you're putting it in a cooler, and if you have sodas or some other beverages or something else where you have perhaps they're at room temperature, if you can get 606,000 joules of heat energy from that set of drinks into the ice, well, you're going to be able to cool those drinks down to a very cold temperature. And that's going to melt the ice, of course. All right, let's take a look at another application. This is vapor pressure. Now, vapor pressure is the pressure that's exerted by a vapor back down on the liquid from which it evaporated. So this is sometimes a little bit difficult to visualize because most of the times we can't see vapor. But if we can imagine a water bottle, and this is a very rudimentary picture, but you can see a little bottle there, a little container, and there's a cap there, and we have some water in here. And that water, we know, is evaporating. Liquids are pretty much always evaporating at normal temperatures. And so we have a little bit of vapor in here. We can imagine that the little vapor molecules are there, and that vapor is actually pushing back down on the liquid. And that helps if we have a closed cap, of course. It has to be closed in order to measure this. But generally speaking, that vapor is pushing down on the liquid. And we may not be able to see that, but it's always there. Now, I think, as you know, as temperature increases, the vapor pressure of the liquid increases. And that makes sense because as we heat up this water, perhaps it's out in the sunlight or maybe it's in a very hot environment. Well, higher temperatures mean we're going to have more evaporation take place. And so more evaporation means more vapor up here and more vapor pressure, of course. Now, here's another factor. If you have a liquid with a weaker intermolecular force, it's also going to have a higher vapor pressure. So if we change this from water to something else, like, let's say acetone, something that has weaker intermolecular forces, well, it's going to evaporate more readily. So yes, it's going to have a higher vapor pressure as well. We look at another factor here. If you have a liquid that has a high vapor pressure at room temperature, that's said to be a volatile liquid. So normally, water doesn't have a very high vapor pressure at room temperature, so it's not that volatile. Acetone, on the other hand, yes, it evaporates very readily. It has a higher vapor pressure at room temperature, so we say it's a volatile liquid. Now, let's take a look at an actual graph of this. Here we have the vapor pressure graphed of 4 different liquids on a diagram here. We have propanone, which we often call acetone. We have ethanol, which is alcohol, water, of course, and then ethanoic acid, which is the concentrated form of vinegar or acetic acid. And we can look at this graph, and we notice that there is a special point highlighted. This dotted line right here, 101.3 kilopascals, that is the normal atmospheric pressure that we consider. That's 1 atmosphere. Whenever the vapor pressure of a liquid reaches 1 atmosphere, we call that the normal boiling point. So for example, water right over here, it reaches that vapor pressure of 1 atmosphere at exactly 100 degrees Celsius. So we can see that. Of course, that tells us that if you lower the pressure in a room or lower the pressure in a container, well, you can also lower the boiling point. So this helps explain why as you go up in elevation in the mountains or some higher elevation area, well, the boiling point of a liquid will get lower as well. Now, the opposite happens too. If you increase the pressure, well, the boiling point goes up, and that explains why people use pressure cookers. So let's estimate the vapor pressure of ethanoic acid at 120 degrees Celsius. So that's a pretty simple exercise. Here's 120 degrees Celsius. So we just go up here to ethanoic acid. And hopefully you can see that that is a little bit less than 110. We can estimate that maybe around 107 kilopascals, somewhere in that neighborhood. At what pressure in kilopascals would water boil at 90 degrees Celsius? So once again, we're going to use the curve for water, except we're going to drop down to 90 degrees this time. So that seems to be right around here. And so that's this point right here. Whoops. So if we look at that and see where that's going to be, it seems like we are right around that spot there. So we can call that about just a tad less than 70, somewhere around maybe 67, 68 kilopascals. And so if you're at a place where water boils at 90 degrees Celsius, the pressure is about 68 kilopascals. How about this question, which of these liquids is the most volatile? Well, we said a minute ago that if something is volatile, that means that it has a high vapor pressure at room temperature. So if we look at just a normal temperature, about 20 degrees Celsius right here, we see that the highest vapor pressure would be propanone. So that's the most volatile. And finally, which of these has the weakest intermolecular forces? Well, the liquid that has the highest vapor pressure also has the weakest intermolecular forces. So propanone is the weakest. I guess that means ethanoic acid would be the strongest. Let's finish up with a few definitions here. Surface tension is the tendency of a liquid to maintain a spherical shape. So if we look at this droplet of water here, we can see that it has that spherical shape because water has very strong intermolecular forces. And so as a result, we can do some neat things with water. I have a different video that talks about this in greater detail, and even a nice demonstration of surface tension as well, how we can make surface tension temporarily defeat gravity. Capillary action is the tendency of a liquid to rise up a narrow tube. So we have some pictures of this, and this works in the case of water here because water actually has a fairly high intermolecular force, but it also has a very strong intermolecular force to glass. Or I should say it sticks better to glass than it sticks to itself. And this works best in a narrow tube, as you can see. So the narrower the tube, the better capillary action works. And so the tube gets wider, well, the capillary action doesn't work quite as well. And so this helps explain why in some plants we can have a little bit of water down here, put some food coloring in there, and we can see the water going up the stalk of celery. So we can get red celery or blue or some other type of celery there. So capillary action helps explain that. There are some other factors at play there in plants, but capillary action is at least a part of it. This also helps explain why if you take a paper towel and dip it into water, that water is going to absorb up the length of the paper towel. It also helps us explain why towels absorb water off your body, off of your skin after you wash your hands or take a bath. So this is a list of some of the applications of intermolecular forces. If you like the video or if you learned something, I hope you like the video and subscribe to my channel.